As always, conservation of energy holds true, so we want to look at how that works specifically with simple harmonic motion. We know from conservation of energy that if we took our potential energy, in this case maybe the form of elastic for a spring moving back and forth, plus our kinetic energy, that would be constant throughout any process, right? We'd always get the same value of energy when you add up the total mechanical energy, assuming there's no losses here. So for elastic potential, right, it's 1/2 kx squared plus our kinetic energy, 1/2 mv squared, is going to equal a constant value. If we look a little further, a really good place to find this constant value and what it would be is when we're at the amplitude, the maximum value for our motion. So if we have a spring moving back and forth when we're at the very ends of our motion, that's a good place to look because all of our energy is in the form of elastic potential and no kinetic, since it stops for that brief moment. So we could say 1/2 kx squared plus 1/2 mv squared equals 1/2 k, I'm going to use a big X squared. And this big X here is going to represent what our distance is for our amplitude. And so this equation here can be used to solve for just about anything throughout its motion. So if we wanted to know, if it has a certain amplitude, but it's only at, say, this position, how fast is it going? Might be a good way to solve a problem here. We could also solve for, right, its maximum velocity. So at max velocity, which is a pretty good thing to be able to solve for, right, we have our equation 1/2 kx squared plus 1/2 mv squared equals 1/2 k times big X squared, our amplitude squared. And when we're at maximum velocity, that means we are at our equilibrium position. So our distance is 0. So 1/2 mv, and I'm going to call it v max squared, equals 1/2 k big X squared. Halves cancel out. And if we solve for v max, that would be the square root, of k big X squared over m. And since the x is squared in there, we can actually pull it out from under the square root and say it's just the square root of k over m times our amplitude. And that's an example of how we could solve for our maximum velocity. We can also do the same sort of thing for a pendulum and say that we adjust a couple things and say that v is actually the length times its angular velocity and the distance it is from equilibrium L times theta, right? Radius times theta, or radius times angular velocity, and substitute those in to this expression so that we have 1/2 k times L theta squared plus 1/2 m times L omega squared equals some constant value. And remember also that we came up with the fact that k for a pendulum was mg over L. So we do some substitutions here and say 1/2 mg over L times L squared theta squared, so distribute the squared, plus 1/2 m L squared omega squared equals a constant. And L is going to cancel out with one of those L's, so we get 1/2 mgl theta plus 1/2 ml squared omega squared equals some constant value. And that's kind of the form that we would use for a pendulum there. So we have conservation of energy with a pendulum, and we have conservation of energy with a mass spring system. And that's how kind of the initial setup that we could use for these types of problems. We could also go through a derivation here to find sort of our maximum velocity, or maybe omega max in this case, and it'd be a very similar thing, but I'll leave that to you to figure out. Damping is what happens when we have some sort of non-conservative work involved with our simple harmonic motion. And eventually that non-conservative work is going to take away all of the initial energy in the system. So whatever our initial 1/2 kx squared is, sort of our initial amount of energy. The non-conservative work will slowly take energy out of the system until all of that initial energy we had in the system is gone. We have three different cases for damping, three different types of damping that can occur. We have underdamped, critically damped, and overdamped. And let's take a look at those three. First is the case of something being underdamped. So this would represent our underdamped motion. What that means is that we're still going to oscillate back and forth, so we still have our usual oscillations here. But over time, those oscillations decrease and decrease and decrease until eventually they would come to zero. Notice that our period for the motion is going to remain the same throughout. So even though our amplitude is decreasing, the amount of time it takes to go back and forth is always going to remain the same throughout this process. That's actually a feature of simple harmonic motion. And it's just going to kind of alternate back and forth until it tapers off. For our other two cases, we don't have that back and forth motion anymore. So here, graph A would represent critically damped. Okay, so critically damped is when you're going to go from your starting position to zero in the shortest amount of time possible. So essentially it's going to come back to zero and stop right there at zero. Our other case, overdamped, means you're usually going to get back to your equilibrium point. Sometimes you may even stop before it. But you're going to sort of drag along the way because there's so much resistive force, so much non-conservative work being done that it's hard to get back to zero. So it gets back to zero eventually, but it sort of drags along the way because of all the resistance it's encountering. And so these are our three cases. We have, right, underdamped, we're going to go back and forth, but eventually to zero. Critically, we get back to equilibrium as quickly as possible. Overdamped, usually back to zero, but not in the quickest time possible because we're going to drag along the way. Resonance is a special case of simple harmonic motion where we're going to be applying a force at a rate equal to an object's natural frequency. So whatever frequency something would normally go back and forth at, so let's take a pendulum for example, right, would go back and forth at a certain frequency, right, back and forth at a certain rate. And what we're going to do is we're going to apply a force at the same rate that this is swinging back and forth. So a good example of this is, think of this being a swing, right? And every time it comes back to this point, apply a force and push. And back to this point, apply a force. Back to this point, apply a force. So every time it's back at this point here, we're going to apply a force. And eventually this motion builds up, from a small motion to bigger and bigger and bigger and bigger. So by applying even fairly small forces, as long as we're applying them at the natural frequency, we're going to constantly build up in amplitude. And that's what resonance is this increasing in amplitude because we're applying a force at the natural frequency. There's lots and lots of examples of resonance that we'll get into, but for now a swing is a really good way to think of resonance.